Okay, so hello everyone. Uh, Today we'll proceed with our lecture in biochemistry, and this will be the start of the topic now for our final. So if you visited your LMS, you can see the result of your exam for the last time. We have chapter 1 to chapter 3, and we're actually ahead now. If try to compare with the other sections, we're actually ahead with the chapters. We're able to cover up until the protein. So for the let me title for the chapter 4. So we will be talking about lipids. Can you see my screen? Okay, so another kind of biomolecule that will be dealt with now that is present in biological systems, now aside from proteins, carbohydrates, we have the lipids. Okay, so can you see my screen? Hindi mo siya next. Okay. Okay, hello everyone again. So I'm gonna be presenting to you that the next chapter is about lipids and part of the biomolecules that's present in our system. I don't know. Next. Next. What's wrong with my laptop? Can you see my screen or anyone? Next. Can you see my screen, guys?
Yes, ma'am.
So again, so what are lipids? No, so we can look at the structure of a lipid. No, usually a lipid is a nonpolar tail. So ang sino mga nonpolar tails? Usually these are the hydrocarbons, katong mga carbon and hydrogens lang that are present. You don't see any other element usually that are electronegative or polar, such as oxygen, nitrogen, and so forth. So those are the nonpolar tail. And part of the structure of the lipids, there is a part of the structure which is polar. So for a polar structure of the lipid, you can expect that there are elements or atoms that are electronegative or that have charges. So the common defining features of lipid is their insolubility in water. So because there is a large part of the lipid structure, that is hydrophobic or nonpolar, and it is for this reasons that lipid is insoluble in water. However, they can be dissolved in nonpolar solvents such as ether, chloroform, and acetone. And if you look at the structure of our lipids, there is a nonpolar tail again and a polar tail, or you call this one as a polar head. That is can possibly dissolve in water, but if the nonpolar portion is so big that it can overpower this polar end of the lipid, it becomes insoluble in water. So since in the structure of the lipid there is a polar and then the nonpolar end, we call the lipid molecule to be amphipathic. Okay, and also we also refer our lipids to be amphiphilic because both the nonpolar and polar end. So lipids are known as fats. Lipids are known as fats. So they have the other names. They're also referred as fats. Provide a major way of storing chemical energy and carbon atoms in the body. So if you remember in chapter 13, we talk about the carbohydrate. It is the energy storage of animals. You have the glycogen, for instance, and it's the main source of our energy storage. But lipids also can provide a way of storing chemical energy in the body. If we will reach the biochemical synthesis, lipids can also be converted into some form of energy. So fats also surround and insulate vital body organs. It's one of the purpose of lipids or fats. Another term for lipids are fats. I'm gonna highlight the fats here. And provide protection from mechanical shock and prevent excessive loss of heat or heat energy. Now, if you notice katong mga niwang nga mga people, right? Pag matugnawan, pag bugnaw ang panahon, dali ra siya mag-chill, because there are less fat, that is present in the body, and the fat actually insulate the vital organs in our body, to prevent protection from the loss of heat. So that's why ang mga tambok okay rin siya pag bugnaw. Also pag ting-init. So examples of phospholipids actually, we have the phospholipids, glycolipids, and cholesterols. These are some examples of the lipids, and we'll look at the structure of this lipids later. And most of these are components of cell membranes. If you remember the cell structure in chapter 1 in biology class, you have the cell membrane, so the one that separates the cell from other cells. You have the cell membrane. The several cholesterol derivative functions as chemical messengers or hormones within the body. So lipids are, of course, found in living organisms. It's part of the chemical reactions. They are family or substance of substances that are insoluble in water, but soluble in nonpolar solvents. We have mentioned that earlier. And solvents of low polarity. So kung naamoy fats, lipids, you notice, of course, the fats, even kana mga fats that you will obtain from our food, like for example, meat, they are hardly soluble in water. Kung magluto mo, maklaro ninyo ang mga luto-luto ng mga fats. They are insoluble in water, but these lipids are soluble in non-polar solvents. We have already mentioned that earlier. So unlike the case of carbohydrates, we define lipids in terms of a property and not in terms of their structure. So on carbohydrates, if you remember, there is a particular structure or sa iyang molecular formula. We have the CnH2O, it's a hydrates of carbon. There is a pattern to the structure of the carbohydrates from the monosaccharides to the disaccharides, the structure, even to the higher. There is always that repeating pattern. For lipids, you couldn't exactly see on their structure, that particular pattern. So we'll define our lipids in terms of its property. But in general, we have already looked at the structure. For as long as you see in the lipid part that there is that soluble end and non-soluble end, or the polar end and the non-polar end. It's what the general structure of the lipids are. So there's a classification for lipids now according to functions. We have the energy storage lipids, so we call that one as the triacyl glycerol. Naka-record. We have membrane lipids. Examples are the phospholipids, the sphingoglycolipids, and cholesterol. And then part of our body we have the emulsification lipids called bile acids. We also have the messenger lipids like the steroid hormones and eicosanoids. And then we have the protective coating lipids or biological waxes. So these are the common functions of the lipids, as well as the examples of the lipids. So if we classify our lipids by structure, we can classify them as simple lipid, such as fats and waxes. And then we can classify by structure the complex lipids. Then there is a different structure for steroids and another structure for prostaglandins, thromboxanes, and leukotrienes. These are usually some hormones. So a simple one are the fats or fatty acids. So the fatty acids are hydrocarbon derivatives. They are carboxylic acids with hydrocarbon chain ranging from 4 carbons to 36 carbons. So what are carboxylic acids? If you look at if you remember your organic chemistry, katong carboxylic acids, katong IC double bond OOH. No? In the structure of fatty acids, na siya chains of carbon, you have from 4 to 36 depende sa length na niya. Or depende if all single bonds, carbon, hydrogen, or na siya double bond. No? Those are the simplest kind of lipids. We call this one as fatty acids. Again, fatty acids are carboxylic acids, ranging from 4 carbons to 36 carbons. The most common biological fatty acids have an even number of carbons between 12 and 24. Very common na siya. Example, kanang mga oils ninyo na ginagamit at home, different kinds of oils. Chains can be unbranched and fully saturated. So like this one, continuous lang ang carbon chains nato, no? Carboxylic acid, and there is a continuous carbon chain. Or they can be unbranched, or it may contain again double bond. So katong mga unbranched and walay double bond, we call that one as saturated fatty acids. No? Just like your hydrocarbons, katong walay double bond, we call that one saturated. Pag na double bond, we call that one as the unsaturated fatty acids. So some fatty acids contain 3 carbon rings or hydroxyl groups or methyl groups branches attached to it. So again, here is an example of the structure of the fatty acid. A saturated fatty acid can be like this one. We don't see a double bond here in the carbon chain, but what you see is carbon-carbon bonds and all single bonds. So the structural formula for 16 carbon, you have this, no? And the structural formula for fatty acid is written in a more condensed form than this one. So you can rewrite this one as a zigzag structure. You've learned that in your organic chemistry. No, you can show all the bonds using the Lewis structure. Or you can use the zigzag structure like this one, or you can use the more condensed form. No? Is you just have this condensed form. The condensed form of the C double bond OOH is COOH. That's for carboxylic acid. And then you have a repeating unit of CH2. CH2, how many? 1, 2, 3, 14, and then CH3. So you can write the structure of the fatty acids as this one. Or you can write a zigzag like this one. So you noticed in the structure of the fatty acids, the general structure, if you remember earlier, that there is a part of the fatty acid or the lipids rather that has a non-polar end, and there is a part that is polar. So you notice in this end here, there is only carbon and hydrogen, and this is the part which is non-polar. This part here is C, this can you call this one as the head. You can see this, there is an oxygen atom here, and of course we learned that oxygen is an electronegative atom. Being an electronegative atom, it draws the electron to itself. So what is the tendency between bonds? It will bear a partial negative charge. And the other end of this, the hydrogen will become partially positive. And in fact, this one is dissociated. The carboxylic acid in water is dissociated, no, this part here, to form C double bond OO minus. So actually, the carboxylic acid in water is dissociated forming actually C double bond OO minus. This one is dissociated, you have C double bond OO minus. There is already a point of interaction of this carboxylic and carboxylate, no, an interaction with water by you have the hydrogen bond, or if it's charged, you have the ionic interaction or dipole ionic interaction with water. And this is the part that can interact with water, but if this part here is very big, no, you can overwhelm this part to this polar. So in the end, the longer the non-polar end of your lipid, the more it becomes insoluble in water. Okay, so even if this part is soluble in water, but there is a big part here that is insoluble in water, the overall molecule is insoluble in water. So again, the first type of fatty acids, if you learn, the simplest lipid is the fatty acids. And for fatty acids, there are two types, the saturated fatty acids, and we'll see later the unsaturated fatty acids. The saturated fatty acids are fatty acids that has a hydrocarbon chain that has no double bond, balik-balik, no? It's I've already mentioned that it's packed close together. It's less fluid, can move as freely, and easily can find for fatty acids that are saturated to have a higher melting point, and it's likely to be solid at room temperature. Pag saturated siya is example, not ka ng mga margarine, right? You notice that it's like more close to solid, no? So it's actually the fat there is actually saturated, and tendency it has a high melting point. For the unsaturated fatty acids, and some na unsaturated fatty acids, kaning na ay double bond. Whenever you see in the structure na kay double bond OO, you have a hydrocarbon chain here. This is the hydrophobic end of the lipid or your fatty acid, and again, this is the polar end. And you notice in the structure is na siya double bond. Okay, so the tendency pag na ay double bond, no, it's you learn in organic chemistry that whenever there is a double bond, it can either be cis, it can either be trans. No, it cannot be a straight chain like your inani, no. So what happened with this is an example of an unsaturated fatty acid. When they are together, unsaturated fatty acids are interacting with other unsaturated fatty acid. What happened is that there is kink. Now there is less organization in the structure of your unsaturated fatty acid in such a way that there is a low melting point for unsaturated fatty acids than the saturated fatty acids, and they are more likely to be liquid at room temperature. Nang ano taas man ang melting point aning saturated fatty acids. Imagine if you have your fatty acids like this, it's linear and it's very organized. When you have a different fatty acids like this in structure, magtapat sila, there will be hydrophobic interactions between the chains of the non-polar end and polar interactions between the polar groups. So there is a greater van der Waals interaction. There are greater forces of interaction between your saturated fatty acids, and because of that, there will be, let's say you have this, no? lang niya isumpay-sumpay. You have this. Okay, let's say for example, you have your fatty acids, no, which is highly organized. There is a greater interaction between the hydrophobic end by virtue of the van der Waals force of interaction. So what happens because of this is that you need a large energy to break this interaction here. And because of that, you expect your saturated fatty acids to be to have a high melting point. If we compare with our unsaturated fatty acids, and for example, makasilingan mo kaning fatty acid, no, will be situated close to another fatty acid like this. So what happens is there is a kink, no, there is disorganization in the structure of the hydrophobic end. So what happens to the van der Waals interactions or the hydrophobic interactions between this nonpolar end? No? Malesen ang iyang hydrophobic interactions because of this disorganization brought by the double bond. And because there is less contact, less interaction with the other inani, with another unsaturated fatty acid chain, no, what happened is less ang iyahang intermolecular force of interactions. What happens is we only require a few less energy to break the interaction of this, to convert this to melt this one. So you expect your unsaturated fatty acid to have a lesser melting point value as compared to your saturated fatty acid. Okay, so when we, again, as I mentioned earlier, our carboxylic acid, this is the polar end, and this is the hydrophobic end in water, no, this carboxylic end will dissociate to form your carboxylate, no. Your carboxylic acid will dissociate to form the salts, the carboxylic saturated fatty acids, and you have your carboxylate, and of course your hydronium ion.
Okay, so repeat.
Okay, so let's have our review first. Let's have our review of your little review of your organic chemistry now. There is a whiteboard. Let's see if I can write on the whiteboard. Let's see. Okay. Let me try the whiteboard. So if you remember your carboxylic acid, let's say the simple carboxylic acid, like your CH3, COOH, okay? And in water, so many, sorry, you have H2O. Nakita ba akong slides? Can you see my whiteboard?
Yes, ma'am.
Okay,
Yes,
so let's say you have your carboxylic. I don't know what. Okay, you have your H2O, no? In water, it will dissociate. It will dissociate to form your CH3, COO minus plus H3O plus. Carboxylic acid actually will be dissociated to form your hydronium ions, and your carboxylate. This is you can have your CH3, C double bond, O, H, right? This is just an acid-base reaction. Remember your organic chemistry. You will have your CH3, C double bond, O, okay, minus. Okay, there is a lone pair there. Of course, oxygen, you expect that there is a lone pair. And plus H3, O plus. This is your hydronium ion. This is the acid part. This is the carboxylate. And this is your, let's say you have your acetic acid or ethanoic acid. This becomes your ethanoate or carboxylate. And this is your acid. So whenever you have your carboxylic acid in water, it will be dissociated to form its anion. This is the anion form, and it will release hydronium ions to the solvent. Okay, so if we have, for example, fatty acids, you expect that fatty acid to be shared to be negatively charged. And so to name our carboxylic acid, our fatty acids rather, the carbon containing the carboxylic group, C double bond OH will be carbon 1. And then the same way that you name your organic compounds is how you name your your fatty acid. But there is actually an accepted name for carboxylic acid, yeah, or common names for that. And usually you have your they say noic acid, so which means that decene you have 10 carbons and octa, 10 plus octa, 8, it's 18 carbons, and we say decene, which means that there is an ene or a double bond in the structure, and oic acid, which means that it is a carboxylic acid. For example, in our ethanoic acid or acetic acid, we end with oic acid. That's for carboxylic acid. So a fatty acid is just a carboxylic acid, and usually in the name you have the oic acid. And depending on the number of carbons is how we name our fatty acid. So here you have 18 colon 1, and you have the delta 9. It means that there are 18 carbons for our fatty acid, and there is only one double bond for our fatty acid. And delta, which means 9, it means there is a double bond on carbon 9. So you can count 1, 2, 3, 4, 5, 6, 7, 8, 9. There is this double bond, and there's only one double bond here. And then you have to say cis if this one is on the cis. So all this R group of the double bond, if they are the same side, we call that one to be cis. And so this is 18, 1, cis 9 octa decenoic acid 9, which means that you have your ene on carbon 9, octadecene, which means there are 18 carbon